All right, guys, we should be about closing out the quiz at this point. Looked like actually activity had stopped a couple minutes ago, so I might have misjudged my time a little bit and given you guys more than you needed, but that's fine. Rather err on that side than the other side. All right, so everybody see my white screen okay?
Yep.
All right, good. Just checking there. I should be recording at this point as well. All right, so what I want to do before we jump back into some Chem 101 practice is to work a little bit further out on this mole concept, which we actually started working with on the video. Now, I limit most of the video content to, I think, jelly beans or something like that that are fun and easy to work with. But then we sort of ended it by talking about how we could kind of move from jelly beans or wing nuts or whatever over to atoms. Okay, so that's really what we want to focus on today. Then once we get comfortable with application of the mole concept to atoms, we can extend it out to molecules and other more complicated things. All right, so remember, we really have two ways that we can think about the mole concept. Okay, I can talk about it in terms of the number of items that are in a mole. So let's just review that real quick. So I can say that 1 mole of any item, which I'll just call X, it could be atoms, molecules, jelly beans, wing nuts, whatever, cats, dogs, is equal to some count of those things, which is 6.022 times 10 to the 23rd of those items, whatever X happens to be. And remember, we have a name for that. We call that Avogadro's number, okay? Now, the other thing that we can do here is we can kind of relate 1 mole or Avogadro's number of things to a mass of those items. Okay, we could do it for jelly beans if we wanted to. If we knew what the average mass of a jelly bean was, I could actually multiply it by Avogadro's number, and that would give me the mass of 1 mole of jelly beans. But I could do it also for atoms or molecules. That's kind of the point. Doesn't make sense in terms of jelly beans. That should be 10 to the 23rd. I don't know why I wrote 12th there. There we go. So for example, if I want to pick, say, a neon atom, so I've just got a periodic table here in front of me, I could say that 1 mole of neon, and I'm talking about average neon atoms here, happens to contain 6.022 times 10 to the 23rd neon atoms. Oh, but now I know what that mass corresponds to in grams. So I go to my periodic table, and the table I have in front of me says 20.1797. And that's grams of neon atoms, okay? So that's what's contained in 1 mole, or 6.022 times 10 to the 23rd neon atoms. That would be the mass of neon atoms in that quantity. Okay, so those are both useful definitions or applications of the mole concept. The other thing that's interesting about this, and I think I mentioned it in the video, is that the mole is the multiplier that gets us from the AMU to the gram. Okay, so we might have learned way back when we were first talking about atoms, that 1 atom of neon has a mass of 20.1797 AMUs, right? But now if I compound that out to 1 mole of neon atoms, that AMU value automatically goes to grams, okay? So we can think of the mole as that multiplier that gets us to from AMUs for a single thing up to the gram equivalent for Avogadro's number worth of them, all right? So those are the 2 useful conversions we're going to use, all right? So now what we want to do is see how we might use them. So our first question here, and this is just an example question, give you guys a moment or two to copy it down while I read it out, is how many moles of zinc, and we're talking about just zinc atoms here, zinc metal, are in a 415.0 gram zinc sample. So we're going to assume here that this is pure zinc. And I want to know how many moles of zinc are in this gram quantity. I got a conversion for that. But the first thing I'm going to do is I'm going to write down my given. Okay, so I know that my given is 415.0 grams of zinc. All right, I'm trying to get to moles, aren't I? So do I have a conversion for anything in the periodic table that gets me from grams to moles? Oh yeah, it's that molar mass we were just referring to that we talked about in the case of the neon, I believe. That gets us between moles and grams. So that I know, for example, for every 1 mole of zinc that I've got, that 1 mole of zinc has a mass that I can look up in the periodic table, right? And my table says 65.39 grams of zinc. Did I say 65.39? Yeah. So notice what happens here, guys. Grams of zinc are going to cancel with grams of zinc. I'm going to be left with moles of zinc, and that's what I want. Okay, so now I can just work that out. And that turns out to be 6.347. And that's moles. Okay, are my sig figs good? Yeah, I got 4 sig figs in each case, so my final answer ought to be good to 4 sig figs. Okay, so everybody see how I use that gram to mole conversion from the periodic table to solve the problem. It's just a conversion factor, just like any other that we've used up to this point. Everybody good? All right, let's take a look at this next simple example. So this one's a little bit more complex because there's a few more steps involved here. And what I want to know here is how many chromium atoms are in a 147.4 kilogram sample of pure chromium. Okay, so that's a lot of chromium. It's a heavy sample of it. So my given here looks like it's going to be the mass of the chromium. So that's going to be 147.4. Let's write that down. We'll give it a unit and an identifier. All right, so it seems to me that we're going to have to go through the mole. Now, the reason I know this is because I'm asking for how many atoms are in the chromium sample. And I know if I go through the mole, I can utilize Avogadro's number because I know that 1 mole of chromium atoms has 6.022 times 10 to the 23rd chromium atoms in it. So I can use that as a conversion to get me from moles to number of things, number of atoms. But in order to get to the mole, I need to do a gram to mole conversion first. Okay, so I really kind of have to use both conversion factors here. Now, the first thing I want to do is get rid of those kilograms, right? I need to get to grams so I can use the gram to mole conversion. So I know that 1 kilogram of chromium has a mass of 1,000 grams of chromium. Okay, keeping that identifier in there. Now I can use the gram to mole conversion. Okay, so I've got grams of chromium. Now I can get to moles of chromium. So I always like to think of mole as my central unit. Okay, so if I'm not sure where to go, you can't go wrong by going to the mole. The mole can get you in whatever direction you need to go. Okay, so from the periodic table, I can see that 1 mole of chromium has a mass of 51.9961 grams of chromium. Okay. So now what you're going to notice that grams of chromium cancel with grams of chromium. I've got moles of chromium now. Now we can use the other mole identity, the one that talks about moles and number of items, to get back to the number of chromium atoms I've got in the sample. And I had to use the mole to get there, right? So I know that 1 mole of chromium contains, because it's 1 mole, 6.022 times 10 to the 23rd atoms of chromium. Okay, so notice now that moles of chromium will cancel with moles of chromium. Okay, so I had to use both types of conversion factors there to get me where I needed to go. And again, my central unit that related everything in this case was the mole. So my advice is, when in doubt, go to the mole, because you can always get in the direction you need to go from there. All right, now work it out. It looks like my sig figs, looks like I'm going to be limited back to 4 sig figs. So when I work this out, I get 1.707 times 10 to the 27th. That's a lot of chromium atoms. Okay. Any questions about that one, guys? Okay, good. All right, another example. So what's the mass in grams of a 1.0 times 10 to the 12th atom sample of pure gold? Okay, so now I'm kind of going the opposite direction, right? I want to go from number of atoms of gold back to a mass of gold. Oh, so what's my central unit going to be that I'm going to work through? What's our central unit? What did we say our central unit last time was, guys?
Moles.
Moles, very good. So we're going to get to the mole. That's ultimately where we want to go because we can get in whatever direction we need to go from there. Okay, so let's write down our given. So I've got 1.0 times 10 to the 12th atoms of gold. I'll just use gold symbol here of AU. So now I can use the mole to get me from number of atoms back to moles of gold. Oh, and once I got moles of gold, I can get back to a mass, right? That's what I want to do. So I know that I've got 1 mole of gold, and in 1 mole of gold, I got Avogadro's number worth of atoms of it. So that's 6.022 times 10 to the 23rd atoms. I'll just bring AU down there. So atoms of gold will cancel with atoms of gold, and that should be a 10 to the 23rd. All right, now I can get back to mass from there by using the other type of conversion that we've got. Because I know that for every 1 mole of gold, the periodic table tells me that I've got a mass of 196 point something, 9665, I think my table tells me. And that's grams of gold, okay? So notice what's happened here. I went from moles of gold now back to grams of gold because I know what the mass of 1 mole of gold is from the table. All right, so again, checking back on my sig figs, it looks like I'm gonna be good to 2 sig figs from my given over there. So if I work this out, it turns out to be 3.3 times 10 to the minus 10th grams of gold. So that's an interesting thing. That's still a lot of gold atoms, isn't it? 10 to the 12th is a lot of them, but is 10 to the minus 10th actually a amount of gold I could weigh out on a balance? Do you guys know of any balance that goes down to 10 to the minus 10th grams? I don't know of any balance that does that. So we're still actually talking about a very tiny amount of gold. So this really gives you an idea of how small and inconsequential an atom really is. All right, everybody okay with that? It's just kind of taking the prior problem and moving it in.
Can I copy it real quick? I'm not done copying.
Of course.
Where did you get the -10?
That came from doing the math. So if I look at this, it's 1.0 times 10 to the 12th. And you guys can check me on this. My math may be off. I can't verify. I don't have a calculator here. Multiply that by the 196.9665, get you an answer. So that's going to be about 10 to the 12th, 13th, 14th. That's going to be about 10 to the 15th. And then what I want to do is divide that by Avogadro's number, which is your 6.022 times 10 to the 23rd. 10 to the 15th to 10 to the 23rd. It's going to still be something very tiny. That 10 to the minus 10th may not be right. Anybody want to verify that for me?
I got 10 to the minus
That's
10.
correct.
Is that okay? Okay, good. So make sure you can do that. I mean, it's kind of looking like, as I was kind of doing the math in my head, that was going to come up to about the right order of magnitude, and that's what I care about. But again, be careful about punching this stuff into your calculator, especially if you're dividing by your Avogadro's number there. You make sure you put that in parentheses when you raise something to a power like that, because otherwise it'll totally confuse your calculator. I know with my TI, whatever it is, I have to do that. Everybody got that one? I know somebody wanted to copy it down. Hopefully everybody got it. Okay. And I think example number 4 is kind of interesting. What's the mass in grams of a single atom of fluorine? Now I'm talking about an average fluorine atom. I could ask this in terms of an isotope of fluorine if I wanted to, but we'll just say an average fluorine atom. What would the mass be in grams? Well, we know it would be in AMUs, right? I would just look it up there in the periodic table. It would be about 18.9984 AMUs. So one way I could go about this is I could look up a conversion between grams and AMUs and do it that way. But an easier way to do this is just to use Avogadro's number, okay? So if I'm talking about a mole of fluorine atoms, what I've really got is, and I'll just write it this way, 18.998. This is right from the periodic table, 403. And that's grams of fluorine, and that's per 1 mole of fluorine, right? So that's the mass of a single mole of fluorine atoms. Okay, now if I want to get to the mass of a single fluorine atom, what would I have to do? Well, I kind of need to get rid of the mole because I'm talking about a single atom. I want grams per atom, not grams per mole. So I'm going to get rid of the moles. So I know that 1 mole of fluorine has a certain number of atoms associated with it. Oh yeah, we know what that is. That's Avogadro's number, 6.022 times 10 to the 23rd atoms of fluorine. That gets my units where I want them to go, right? Because what I really want is grams of fluorine per atom of fluorine, and that's where the units take me. So the moles are going to cancel out. So now I'll have the mass in grams of a single fluorine atom. And it turns out to be, we got a ton of sig figs there. 3.154, and we're going to assume Avogadro's number is not limiting us here. 8328 times 10 to the minus 23rd. And that's grams of fluorine per atom of fluorine. Okay, and that's what the question asked me for. Okay, I think the sig figs worked out. 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. Yeah, we're good. So that's an alternative way to get there if I didn't have a direct conversion factor between AMUs and grams. Though there is one, you could go look it up. It's probably in your textbook. But this is just an alternative way of getting to the same answer. All right, everybody good with that one? All right, we got a few minutes, so let's pop back over to Chem 101 here for a bit. I'm still going to screen share. And I'm going to open up an in-class practice here. And this is over in chapter 2. Might be chapter 3. Sorry, I'm into the next one. I got to open up the chapter 3 homeworks too, guys. And let's just start the mole concept one here. There we go. So it's about a 10-minute one. So it's going to turn out to be almost exactly right in terms of the time we have left here. A couple of these are just definition-based things, and others are just some similar kinds of problems to work out as the ones we were just doing. Number 2 is a lot like your quiz question, but oh so slightly different because this one's referring to a specific isotope of carbon. So watch that.
Can you do number 4?
Sure, we could do number 4. All right, so let me pop out of here and back over to and I'm just gonna have you relate to me what's in there once I get my notes up here. Okay, so what's given in the problem? Just kind of yell it out to me since I'm not looking at Chem 101 anymore.
It asks how many moles of calcium atoms do you have?
Okay,
3.00 x to 1021
and that's atoms of
atoms
calcium.
of calcium, yeah. And then it asks
Okay.
the mass of 1 mole of calcium is 40.08 grams.
40.08 grams. And that's right out of the periodic table, right? Okay. So now we got atoms of calcium, and I want to get back to moles of calcium. So I got to go from atoms to moles. Okay. So what's my conversion factor that gets me from number of things to moles? Would I worry about the gram one there?
Would you put
Five?
Avogadro's number?
Yeah, and it's going to go top or bottom.
The bottom.
Yeah, let's put it in there. And now that's how many atoms I've got in 1 mole of calcium, right? So look what happens. Atoms cancels with atoms, and I'm left with moles. So if the question was asking you for how many moles of calcium, this is all you'd need to do. Now, if it wanted to know how many grams of calcium were in the sample, then we would need that other conversion factor there, right? That takes us from the moles to the grams. Okay, but if you're just looking for moles, you're done. Does that make sense?
Yeah, thank you.
You're welcome. Okay, see how we're doing. Yep, that's interesting. They kind of gave you a little bit of extraneous information in that problem, didn't they?
Can I still see that problem on number 4?
Yeah, I can take you back there. That's it under the squiggle there. You got it?
Yeah, thank you.
You're welcome, sir. I'm just gonna run back and see how we're doing here. Yeah, we're making progress. Okay, guys, as we're closing out here, just a couple reminders for Monday. I will remind myself to open up the chapter 3 homework because I know folks like to work ahead and practice using the homework there. So I want to open that up so you can do that. The other thing is keep in mind, you got another video for Monday where we're going to just sort of extend this over into molecules. Okay, so everything that applies to atoms also applies to molecules. And that video will start to introduce that for you. I believe that's the one we're talking about. And then be ready for a standard 5 for 5 quiz, a little short quiz on Monday. Anything else, guys? All right, if there are no other questions, you guys have a wonderful weekend and stay warm. We'll see you on Monday.
Thank you.
Thank you.
Good as well.
You're very welcome, guys.